Hi everyone, my name is Reef James, and today we're going to be getting learned all about antennas. What is an antenna? How it works? Kind of the fundamentals of antennas, right? Get you up on your knowledge on the fundamentals. And once you have that, base level knowledge, you're going to be able to use that knowledge to make an informed decision to decide whether a certain antenna might be more suitable for your circumstance, okay? Okay, so just as a TLDR, if you don't care about how antennas work or anything like that, basically, ballpark, if you have between 10 and 20 hotspots within a few kilometers radius of your house, go with a low gain antenna, right? That's better for the Helium network. It's better for serving LoRa devices around your area, and you don't need a high gain antenna to talk to other hotspots because there's plenty of them close to you. But if you're in an area where you don't have a lot of hotspots within a couple of kilometers radius of your house, you might want to consider going with a higher gain antenna like a 5.8, a 6, or maybe a 9 dBi antenna, okay? That's the TLDR. Back into it. I just need to say, to begin with, right, there's a lot of YouTube videos out there where people are just saying, this is the best antenna. That specifically, this antenna is the best helium mining antenna, right? This one. Anyone who says that, they either don't know what they're talking about, or they're dumbing it down for you, right? You're not a stupid person, okay? You're here to learn, and you want to be able to use the knowledge that you learn in these videos to make an informed decision, right, on what is the best hardware for you, okay? You're spending hundreds of dollars on gear. You don't want to be spoon-fed dribble information, right? You want to know what's going on, okay? You're not an idiot, right? And the other category is they might be affiliated with the antenna manufacturer, okay? So they might be getting a bit of a kickback from the manufacturer, or maybe like a local reseller or something like that. So anytime anyone says, you watch a video and they say, this is the best antenna, just click in your mind that you're either being spoon-fed information, they don't know what they're talking about, or they're probably making money off the sale of that antenna, okay? And that doesn't necessarily mean that the antenna that they're pushing is a bad antenna, right? Very likely it's going to be a good antenna that will work for a lot of use cases and a lot of different situations, right? But touting and saying that this antenna is the best antenna for everyone, that's just not the case, okay? That's just not how it works, right? I do RF engineering for work. I do RF planning. I play with antennas for work. This is what I do, right? You have different antennas for different use cases, okay? So just blanket saying that this antenna is the best antenna for helium mining, it's just not the case, right? Everyone has different environments, okay? This guy is out in the flatlands, right? This guy, he's up in the mountains. This guy is surrounded by trees, big tall trees, and this guy is in a dense urban environment, right? Different environments are better suited to certain types of antennas, certain characteristics of antennas, okay? So we're gonna try get your knowledge up to the level, so you might be able to make a bit more of an informed decision when purchasing an antenna, okay? So let's just start off with what is an antenna, okay? What actually is an antenna? So at a base level, like a very low level, an antenna is a piece of metal that resonates at a certain frequency. So what does that mean? What does it mean to resonate at a certain frequency, okay? Well, you hear the word frequency and you might know what that is, you might not. So frequency is just basically how fast something happens, okay? So if you hear the word frequency, for instance, 900 megahertz, right? That's what the roundabouts, what the LoRaWAN frequency is. It changes depending on your region, but let's just say 900 megahertz, okay? So 900 megahertz, mega means million, so 900 million hertz. That means that the signal oscillates, goes up and down 900 million times per second, right? Because 1 hertz, it's literally the SI definition of frequency. And that definition is how many oscillations over a length of 1 second. So if you have 1 oscillation, you go from peak to peak that takes 1 second, well, that's 1 hertz. If it does that 900 million times, which is a roundabout ballpark where the LoRaWAN frequencies are, well, that's the frequency. And that frequency corresponds to a physical wavelength, right? A physical size. That physical size is the resonant frequency of your antenna. So if you have a physical size of your wavelength and that matches the physical size of your antenna, well, it's going to resonate, right? There's a lot more that goes into it, but at a base level, that's kind of how it works, okay? So for instance, right, let's have a look at this here. This is just a little brass rod that I had laying around back there. Let's measure this up. So this is, stop detecting my face. What's that? 1335. Okay, so that's like 135 millimeters. Let's jump over to the computer here and we'll do a bit more of a deep dive. All right, today's tomorrow. We had some technical issues last night, but let's not worry about that. We're going to jump into this Excel sheet and just explain how frequency relates to wavelength, relates to antenna size, and just a bit of the nomenclature that we use in RF engineering to talk about big numbers, right? So let's jump into it here. So I've set up this little Excel sheet with a couple of calculators here, defining what a wavelength is here, and then a bit of the engineering nomenclature here that we use. Let's start off with the engineering nomenclature, the good old fun stuff, right? The main ones we're interested in here is kilo, mega, and giga, right? And basically all it is just shorthand ways of saying big numbers, more or less, okay? So if you see kilo, it just means, a multiplier of 1,000, mega, multiplier of 1,000,000, and giga, multiplier of 1,000,000,000, right? So if you see over here, the frequency is 900 E plus 6. Plus 6 is million, or mega, so 900 megahertz is the frequency, right? If you see 2E plus 9, which is 9, which is billion, which is giga, so 2 gigahertz is the frequency. It's just easier to say gigahertz and megahertz instead of, like, for instance, it's easier to say 900 megahertz than it is to say, 900 million hertz, right? More better. Anyway, what is a wavelength? Well, a wavelength is defined, it's the length of a wave, right? From peak to peak. You go peak, trough, peak. That is how long a wave is, right? And if the frequency is higher, as in it's happening more and more quick, right? The wavelength is smaller. All right, this is Editing Reef here. Upon reviewing that footage, I thought that I'd more better be able to explain frequency and wavelengths with a nice little animation that apparently took me about 10 hours, right? So it took me a little while to learn how to code and animate some sine waves in After Effects, but here we are. Let's get into it. So before we start, let's just lay down the law that the definition from the left side of the screen to the right side of the screen, that amount of time is 1 second, right? So if we have one wave within the screen, that is 1 hertz, okay? So let's play. So here we can see that there's 1 wave in the screen, so that's 1 hertz. And then we can double that. Now we're at 2 hertz. You can see there's 2 full wavelengths in the screen. Double it again. We're at 4 hertz, okay? 8 hertz, 16 hertz, 32 hertz, 64 hertz, and so on, right? So you can see that the same amount of time is sticking. That 1 second from the left-hand side of the screen to the right-hand side of the screen is the same. We've gone all the way up to a super high frequency here. You can't even see the data, and we're bringing it all the way back down to our single hertz right now. Here we are, back at a single hertz. So I hope you appreciated the animation. Thank you. How you calculate it specifically is if you have, for instance, if you have the frequency, your transmission frequency, and you want to calculate the wavelength, well, you just put the speed of light over your transmission frequency. All right, so we have our constants down here, which is the speed of light, which is about 300 million meters per second. So yeah, that's how we do that. If we want to calculate wavelength, speed of light over frequency. And same deal here with frequency. If we have a given wavelength or a given antenna length that we want to know what the resonant frequency will be, it's just speed of light over the wavelength, right? So what we're looking at here is 900 megahertz, which is roughly what the LoRaWAN frequency is, roughly, depending on your region. But that corresponds to a resonant frequency of 0.33 meters, a bit over 30 centimeters, right? So roughly, this metal ruler here, it's a bit over 30 centimeters, right? It's 30 centimeters plus this little bit at the end, right? So this would ballpark work as a shitty LoRaWAN antenna or Helium antenna. If we soldered an RF connector onto this, it would probably work as a really shitty antenna. Okay. All right. Let's have a bit of a play. So if we have an antenna of a length of 1 meter, right? What will its equivalent frequency be? Like, what would it most efficiently absorb? So let's put in 1 meter. A wavelength of 1 meter, and that corresponds to 299.8 megahertz, so around about 300 million hertz, 300 megahertz, right? So that means that an antenna length of 1 meter would roughly resonate with a transmission frequency of 300 megahertz. Now, let's dive into a bit of a practical example here. We're going to go through this little video here, and then at the end we'll come back and have a bit of a chat about why it's doing the things it's doing, and just kind of understand it a little bit, right?
Tower, 50 kilowatt tower, and basically what it is the tower itself is the whole underground is the dish, and the tower itself is the feed horn. So when you remove these right here, it's basically electrical current that's running through these. So we're just going to take this one off right here. Refinance today. Rates are below. Woo! That fucker jumped up there. Competitive rates 143609000. Alliance Mortgage provides it. Anyways, if I do it too long, it'll freaking burn it up. 3%. 43609,000.
Do not touch. This is why you do not ever touch an AM tower.
That's right.
All right, that was pretty awesome, right? What we were looking at there is an AM broadcast tower that wasn't live, right? But that whole thing that you were looking at there in the video, that was the antenna itself, right? That you might have thought that is the tower with the antenna on the top, like at the mast, right? But no, that whole massive tower is the antenna, the radiating element of the antenna. And what we were looking at there, that transmission tower was powered off, right? But because it was such a big antenna that resonates with the transmission frequency of the AM towers that are broadcasting around it, it was picking up all that RF energy. And old mate, when he was taking that clamp off there, the energy was being absorbed by the antenna and then arcing across to get into that clamp that was going down into a ground rod, into the ground. And you heard the sound, right? You heard the radio. I'm not 100% clued up on what's happening there, but somehow the plasma, the arc is demodulating the AM broadcast frequency, right? I'm not exactly sure what's going on, but that's happening somehow there, right? So, what is the transmission frequency of these big towers, right? Well, that tower was WMVP over in America, and their transmission frequency is 1,000 kilohertz, right? Or 1 megahertz. It's the same number. Now, what does that correspond to in antenna size, right? Let's have a look. So we were 1000 kilohertz, right? So let's write 1000 E3, which is kilohertz. And it puts it to 1 E6, which is 1 megahertz, the same thing, or 1 megahertz, sorry. And the equivalent resonating, the wavelength of that is around 300 meters. So that means you would have to have a perfectly resonating frequency. You'd need to have an antenna that is 300 meters tall, right? Well, if we have a look at the height of these antennas, that specific tower, you can Google this, it's WMBP, AM broadcast tower, that is 499 feet tall, okay? And convert that to meters, that's around about 150 meters, which is half of the perfect resonant frequency of what you would need, right? 300 meters would be a full wave antenna, okay? Well, you don't need to have a full wave antenna. You can go down in certain increments of the antenna's full wavelength, and you can still resonate, quite well with that frequency. So that antenna, that huge AM broadcast tower, is 150 meters high, which is half of the perfect resonant frequency, which is 300 meters, okay? So that is a half wavelength antenna, okay? And they could have had another one, which is half of that again, 75 meters or whatever, half of 150, and that would have worked, quite well as well. So you can see that transmission frequency and antenna size really, really does matter. Like it's a big deal, but that's how it works, okay? So, and a transmission frequency of 1 megahertz, you need an antenna size of 300 meters to get a perfect, full wavelength antenna. Whereas if we look at our helium mining or LoRaWAN frequency, which is 900 megahertz, which is, 900 times higher frequency than this, as in it switches 900 times quicker than this. Let's put it in, 900 E6. We have an antenna that needs to be 30 centimeters long, right? Compared to 300 meters, right? So transmission frequency really, it determines how big your antennas are. The higher the frequency, the smaller the antenna, okay? It's pretty cool stuff. All right, so we're just going to go down a little tiny rabbit hole here with regards to transmission powers and kind of compare the helium transmission powers compared to these AM broadcast transmission powers, right? Little bit of a rabbit hole, but we're just going to be looking at dBm compared to watts, which is the same thing, right? It's just another measurement of power, but we're just going to illustrate it here graphically so you can kind of intuitively understand what's going on, okay? So we have dBm, milliwatts, and watts. They're all a measurement of power. dBm is logarithmic, where power in milliwatts and watts is linear, right? Okay, so we have 1 dBm all the way down to 77. So 77 dBm is what these AM broadcast towers transmit at, okay? That's the amount of power that they're pumping out into the air, okay? So let's just compare them, right? So if we put in, let's just leave it at that, 36 dBm is 1 watt, okay? 1 watt of transmitted power. And if we put in 77, we have 50,000 watts, right? A big deal. Now let's just look at this graphically and try to understand in our head how big of a deal that is, okay? All right, so looking at this AM broadcast power chart here, both axes are power. The bottom is dBm and the left axis there, the vertical axis, is power in kilowatts, right? Thousands of watts. And you can see that it ranges from 1 to 77 dBm. So you can see that your rough transmission powers of, at least in Australia and America, it's about 36 dBm, depending on where you are. And then in Europe, it's down around 16 dBm. So you can see that that's basically flatline compared to AM broadcast powers, right? Now, if we scale that down to sort of what your typical telco transmits at, so we can see roughly from 1 to 46 dBm is around about where your telco will be transmitting it at full power. Depends on where you are, but just ballpark figures about this, right? So we can compare your transmission powers of your telco at full tilt, which is around 40 watts of transmission power, compared to your Helium miner at full power. If you're in America, you know, around about down here, around about, you know, 4 watts-ish, give or take. And then if you're in Europe, you're basically still flatlined. Now let's scroll over to the LoRaWAN. So we look at LoRaWAN, we have 1 to 30, well, 36-ish, and you can just see how the power levels, the transmission power levels scale. So you can look at 16 dBm compared to 30 dBm and just really visually see how much of a power difference there is there. Pretty interesting. All right, now we're all learned up on antennas and you know roughly how they work, right? What is the best antenna for helium mining? Well, like we said at the beginning, it depends on where you are, right? So if you're in an area where you're in a fairly dense urban environment and you have a lot of helium miners around you, say within a few kilometers, you know, less than 5 kilometers, maybe you have between 10 and 20 other helium gateways, right? Then I suggest that you go with a low gain antenna, okay? Because the idea of the helium network is to build a mesh network, build a network around the area. So if you have a low gain antenna, you're serving less of an area. Your RF energy is being pushed out only within a closer proximity of your area. So you get a better coverage closer to you, right? So if you have lots of other hotspots around you serving the area, that's what you want to do, because you'll still be able to talk to them. You'll still be able to get, you know, proof of coverage. You'll be able to witness them and you'll be able to make money doing that. And you'll better serve the LoRa devices in the future that are going to be, you know, roaming around that area using the network. But if you're in an area where you don't have that many other helium miners that aren't really close to you, then you're probably gonna want to go with a higher gain antenna, right? Like a 9 dBi antenna, depending on your area. But you'll overshoot hotspots that are near you. Blah blah blah. No, like you won't, right? I've spoken to so many people on the Discord, and heaps of there's just an assumption that's the case. Well, if you want to pause this and then have a little look at that there. That's the trigonometry that says otherwise, right? So if you have an antenna that's 20 meters high, right, and you're using a 9 dBi antenna that has a vertical beam width of 12 degrees, well, you can do the trigonometry and see how far away that signal will be hitting the ground, right? 190 meters, right? That's if your antenna is 20 meters up in the air. So if it's less than that, it'll be hitting the ground. Your signal will be hitting the ground closer than that as well, right? And there's a lot that goes into it, but basically it's a non-issue, right? These helium hotspots are supposed to be more than, or at least 300 meters away from each other, right? And they're also not on the ground. They're up higher as well. So you see what I mean, right? The overshooting thing with high gain antennas is not an issue. Editing Reef back here again. The overshooting is not an issue if you're trying to, you know, at this point in the Helium network where we're just, you know, providing proof of coverage and really the network is not being utilized at the moment, the overshooting issue is not a big deal because you're going to be able to talk to other Helium hotspots, right? The issue, you know, you might not be serving the area right directly around your house as well as if you had a low gain antenna though. So like if someone was using the Helium network and they had a device, you know, that they were walking around your house, they might not be able to communicate with your gateway as well, right? That's an issue there. And one more quick little thing here that I didn't really go through in the video here is the gain of the antenna doesn't determine, like it doesn't inject power into the thing. All it does is concentrate the RF power that's being transmitted from your radio into different areas, right? So if you have a low gain antenna, it has the same amount of power, it's just concentrating that RF power closer around your antenna. Whereas if you have a high gain antenna, well, it kind of squishes that power out so you can kind of shoot it further, but it's the same amount of power, okay? All right, let's go back. The issue with using a high gain antenna is that you might get a really good RSSI when beaconing other close antennas, close helium hotspots. And if you have a really, really strong signal, then you may be flagged as invalid, right? So it really comes down to trial and error. If you don't have any hotspots close to you, then go with a higher gain antenna, and you shouldn't be getting invalid witnesses. But if you use a high gain antenna and you have lots of other helium hotspots that are around you, then there's a decent chance that your beacons and your witnesses will be flagged as invalid and you won't earn HNT, okay? But in that case, just go with a lower gain antenna. Now, with POC 11, where they're limiting your transmission power dependent on the gain of your antenna and your with your cable losses included and all that sort of stuff, right? With Europe, with their such low transmission power of dBm of 16 EIRP, right? I would suggest using a higher gain antenna, right? Because even if they're limiting the transmission power, so if you have a radio that has it transmits or it produces 16 or 14 dBm, right, of power, and then you have a 9 dBi antenna, well, that brings your total transmission power, your EIRP, sorry, higher than the limit of 16, okay? So they'll throttle your transmission power down to meet the EIRP of 16 dBm, right? But the gain of that antenna still counts on the uplink side, right? It still counts on the receiving side. So if someone sends out a beacon, right, you can essentially hear the signal better with a higher gain antenna, right? Because you still have that gain that comes into effect and plays on the receiving side. And that's important, especially over in Europe where your transmission powers are so little. You really want to be able to hear those little transmission powers, right? So I would say in America, you're probably, and Australia, you know, maybe your 6 dBi, you know, probably lower ones. But really, again, it depends on your situation and your area, as we discussed earlier. If you have a lot of hotspots that are around you, sit with a lower gain antenna. You do not need a higher gain antenna. But if you're, you know, in a country town and there's not that many people, then by all means, get a high gain antenna, right? You're gonna get a better RSSI. You're gonna be able to beacon more hotspots because you don't have them close to you. You need that gain, okay? And if you do start getting invalid witnesses, well then get a lower gain antenna, okay? And another rule of thumb is get your antenna high, right? You really do want to get line of sight to as many neighboring gateways as you can. That's super duper important, all right? So if you're in a dense environment with lots of hotspots, low gain. If not, high gain. You're not going to be overshooting. Don't worry about that. If they limit your transmit power because you have a high gain antenna, don't worry about that. You're still getting the benefits of being able to use that gain to receive and listen to signals at a lower level. If you're worried about signal to noise ratio and all that kind of thing, you're having these signal to noise ratio issues with whatever gain antenna you've got. If it's a big deal, then you can look into other means of mitigating that using band pass filters, but that's out of the scope of this video. We might cover it in another video though. So thanks for hanging out, guys. I appreciate you. Share this around to other Helium friends and join the Discord, right? I've made a Discord channel. If you have more questions, post in there and I'll answer when I can, right? Subscribe. like, and if you have any questions as well, just comment here. I'll respond when I get time. Thanks for hanging out, guys. Appreciate you.